Hello, welcome to a video that covers section 3.3 on differentiation rules. So we're going to find that some of these rules are going to enable us to take the derivative quite effectively. Definitely we used the limit definition for the last couple weeks, but now you're going to be able to do the derivative in a way that will be not as long or painful, if you want to think of it that way. But first off, we know the limit definition of the derivative to be the following. The limit as h approaches 0 of f of x plus h minus f of x all over h. Now, if we look at the first derivative, if we look at the first problem, so the first derivative problem we're trying to do here, that's like saying y equals 7. Of course, we know that just to be a horizontal line, so we expect this answer to be 0. If I were to actually do the limit definition, so remember f of x plus h minus f of x all over h, well, here's the deal. Your output's always going to be 7. So whatever this is, whatever that is, they're always going to equal 7. So you got 7 minus 7 over h. Taking the limit as h approaches 0. Well, basically, you just got yourself now the limit as h approaches 0 of 0 over h, which just gets us 0, because 0 divided by anything is 0. So what this tells us that if you ever have a constant function, so there's no x, y equals 7, y equals 10, y equals 4.783, some random constant, your derivative is always going to be just 0. That's because the slope of a horizontal line is 0, and we know the slope of a tangent line to a function is just going to be, of a horizontal function is just going to be 0. Now, what if f of x equals x? If I do this using the limit definition again, okay, we are going to get the shortcuts, trust me. So again, f of x plus h minus f of x all over h. So the output, when the input's x plus h, is going to be x plus h, because remember, f of x equals x. Whatever you put into x, that's just going to be the same y value. So if the input's x plus h, the output's also x plus h. And of course, when the input's x, the output's x. Don't forget your limit notation. So the x's just cancel. Now you're taking the limit as h approaches 0 of h over h. Of course, that's just going to be the limit as h approaches 0 of 1. And that's just 1. Now, we have done x squared and x cubed before. X squared we know is 2x. That's from an old note or homework, I think. X cubed we've done many times. That's 3x squared. So hopefully you can see a pattern. When you have plain old 7, that's like saying y equals 7 times x to the 0 power. You could write it that way, because anything to the 0 power is 1, and 7 times 1 is 7. Of course, this is like saying y equals x to the 1 power, and you have that function. And then we have y equals x squared, y equals x cubed. So what we're starting to notice is that maybe we can just do some of the exponents and the coefficient and get the answer. So for problem number 5, what if we realize that the exponent just moves to the front and we drop the old exponent by 1 to get a new exponent? So we hope we can see that kind of conjecture. X squared is 2x, x cubed is 3x squared, x squared 4x cubed. So moving the exponent down, in front of x, and dropping the exponent by 1, and of course, whatever coefficient you have, multiply by that. But let's work out problem 5 by hand really quickly, using the limit definition, and see if it's going to equal 4x cubed, and maybe our conjecture is true. And then we have a shortcut. So you'll probably be really glad once you finish this one, because once I show you the shortcut rule and prove it, then you're probably just going to use it all the time, unless I ask you to do it this way. So we got to plug in x plus h in for x. So basically it's x plus h to the 4 power. Ugh, that's crazy. And of course minus x4 all over h. Don't forget about your limit notation. So here is what is going to happen. If we do the expansion, which is shown right here, that's going to be x to the 4 power plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h4 minus x4, because the x4 from f of x, all over h. x4's cancel, which is nice. And we can probably factor out h. So you get 4x cubed plus 6x squared h plus 4x h squared plus h cubed all over h. The limit as h approaches 0. Oh, look at that. Those h's cancel. If I plug in 0 in for h, I'll get 4x cubed. So this leads us to a huge revelation. If you're taking the derivative of x to the n power, the derivative is going to be n times x to the n minus 1. That is huge. So you simply move the exponent to the front, drop the exponent by 1. Or if you use a different notation, d over dx, same thing, right? Just different notation. So if I ask you to do x to the 8, why use the limit definition? Because that's going to be way too crazy. But just 8x7. For problem 7, now here we have 11 times x to the 4. Now, I am saying to use the definitions of the limit. Okay, let's do it. So you got this. Now, I'm going to have 11 times x plus h raised to the 4 power. Minus x to the 4. Sorry, minus 11x4. My bad. Over h. Limit as h approaches 0. Again, that's an 11 right there. Make that a little more clear. So f of x is 11x4. We know that. And of course, if you replace x with x plus h, then you get x plus h to the 4 power times 11. Now, what if I factored out the 11? Kind of just pulled it out like that. Now we got ourselves this. And these are limit definitions, right? Where we can actually say that, right? 11's a continuous function, and x to 4 power is a continuous function. We could totally separate our limit in this manner using the stuff we did from the previous unit. And we already know what's going on with x to the 4 power is 4x cubed. So boom, there we go. And the limit of a constant is just going to be the constant, right? If h is approaching 0, then that's just plain old 11. So you wind up getting 44x cubed. So what this tells us is that if we have a constant multiple, so you have a constant being multiplied to your function, it's simply going to be c times the derivative of u with respect to x, or you can write as c u prime. So in the case of right here, it's going to be 1/5 times 7 times x to the 6th power. Focus on x to the 7, take derivative using the power rule right above, right? But drop the exponent, or remove the exponent to the front, drop it by 1, and of course you have 7/5 x to the 6. Also, if we're adding two functions or subtracting two functions, and we're asked to take the derivative of the sum or difference, just take them individually. Like in this case, that's like saying y equals 1/2 times x to the 4 plus 1/3 times x to the 9. So simply I'm just going to, take derivative of x to the 4, which is 4x cubed, and keep it multiplied 1/2. Take derivative of x to the 9, which is 9x8, but keep it multiplied to 1/3. And got 2x cubed plus 3x8. So again, a lot of this is just mechanical, just kind of going through the motions. Once you get really good at this, you can move pretty quickly. So the derivative for number 10 will be 30x squared minus 12x plus 5. Very nice. Now if you're asked to find the equation of tangent line to this function at x equals 0, remember the slope of a tangent line is the derivative, right? So we'll just do that. So I'm going to plug in 0 into my derivative function. So apparently the slope of the tangent at x equals 0 is going to be 5. So when I write the equation of my line, which we use point slope form, this tends to be a little easier. And when x is 0, apparently the y value is 13. So I got y minus 13 equals 5 times x minus 0. And that's the equation of the tangent line for f of x at x equals 0. Lastly, we get problem 11. You have to find where there are horizontal tangents. That means that your derivative is going to equal 0, right? Because the slope of a horizontal line is 0. And of course, that means the derivative is also going to be 0, because slope of tangent lines and derivative values, same thing, right? We can do this without using a calculator. I think we can handle this. So first of all, let's take our derivative. 4x cubed plus 4 thirds times 3x squared minus 24x. Okay. And of course, plus 0 because 7 is just 0. Clean up a tad. Lovely. And set this sucker equal to 0. And simultaneously, I'm going to factor out 4x. And then do some, factoring with the trinomial, which you guys should be pretty comfortable with. You've done this since middle school. Now when you ask, why do we have to use factoring? Now you know why. Of course, you may still think it's not useful later in life, but whatever. So those are the places. Because they said find where, it means I want the x-coordinates. I want the places where I can have horizontal tangents on that funky curve. And you get 0, negative 3, and 2. You could graph this in the calculator and kind of see for yourself. In fact, doing a little bit okay on time here. So if I were to plot my function, and it's a little bit painful to do this in the computer, but we'll do it, because I said I would. Plus parentheses 4 thirds. By the way, I'm in the old operating system mode. So if you hit mode and then go down and switch math print to classic. So mode. See, I'm in classic. I'm doing classic because I want to make sure you guys can see what I'm doing, because in the math print mode it doesn't show all the lines. It kind of just hides what you typed in previously. So I want to make sure you see what I'm doing. Okie dokie. Now, I'm also going to graph in the standard window. Let's see what happens. Change the window a little bit. I don't know, let's do like negative 20 perhaps. Okay, well I definitely see horizontal tangents at probably 0 and 2. Kind of hard to tell with the other one. So let's try this one more time.
At the beginning of class, rather than this, do you want to go to French class or be with me? I think French class.
And that was Ms. Farrington Padilla, who was talking to an exchange student. So,
Talking very loud.
Anyway, we still can't quite see the other horizontal tangent. But we could do is do second trace maximum. Because usually that's going to happen at maximums. If we go left and right of the first maximum, or the only maximum we have, you do get pretty much something that's close to 0. Another cool thing you can do too is you can select option 6, dy over dx, and actually plug in, like, say, 2 to see what the derivative is supposed to be. And it gives you a really small number. Remember, it's doing an approximation. We talked about the algorithm the calculator uses when it does derivatives. It does a symmetric difference quotient. Yeah, that looks good. Or if I want to do it again and type in -3, it gives the same thing. So we feel pretty comfortable we've done this right. So you can use a calculator to verify your work. Okay, I think I'm done with the video. And have a great day, great weekend. And lastly, I tend to do this for most of my videos during the college football season. I'm going to give a prediction for the Stanford and UW game. UW, University of Washington. I'm going to be bold here. I'm going to say 34-20. And Christian McCaffrey will have 150 yards at least and 2 touchdowns. And our Sacred Heart alum, Ben Burkervin, we'll say he gets 6 tackles. So he plays for UW, in case you didn't know. He's a linebacker. Okay, looks like we're all set. Enjoy the weekend, and I will see you guys later.